So when we go from lower frequency to higher frequency, okay. So this lumped element filter design, so at low frequency it will work, but the parasitic effects it will going to alter the response of the filter at the higher frequency. So one of the problem is, so as I said, lumped element inductors and capacitors are generally available only for a limited range of values. That means at the lower frequency, say up to some, maybe it may work up to say some 900 megahertz, 700, 800 megahertz like that. So when you go beyond that frequency at the micro frequency, so this lumped element filter designs it is difficult to implement. So no longer the capacitor will work as a capacitor, whatever the value will going to give. Okay, so that is a problem. So that's why when we go for the higher frequencies, so these distributed elements such as open circuit and short circuited transmission line stubs will be used, so instead of the lumped elements. Okay, whatever we calculate the lumped elements design in the circuit, so that it will going to transform into a stub design. So that is a kind of transmission line. So in microstrip version we'll going to so transform. So in order to transform that, so what are all the methods they will going to use? So that is what the important thing. So here the first problem we can treat it with the Richard transformation, where we can convert the lumped elements into a transmission line sections. So that is a one transformation we can do. Another one, so the CUDA's identities, so that is another transformation. We can physically separate the filter elements, so by using this transmission line sections, or we can use stubs, that is open stubs or short circuited stubs. So now the whatever the additional transmission line sections which we can use to transform from whether it is series inductor to some kind of stubs, so where we can use this kind of transmission line section, that we have to insert in such a way that that should not alter the filter response. So that additional transmission line section, so where we can able to convert that, so the lumped elements to a stub design, so that should not alter the filter response. Like that we need to add the transmission line sections. So this type of filter synthesis which is called as redundant filter synthesis. Okay, so redundant filter synthesis, we'll see one problem how we can add those redundant transmission line section to convert the complete design, so from lumped element to the so stub design. So that one problem we're going to see. Okay, so now we'll come to what is the Richard transformation. So here, so earlier we have the omega, the cutoff frequency or the frequency of operation in terms of omega is there. So now in Richard transformation, what we will do, we will map the omega plane into that this omega plane. Both will be call it as omega plane only. But this omega plane will be acts in terms of lumped element frequency design. But here this omega, so which will be tells us the distributed element frequency. So that will be call it as normalized frequency. So where, so in the stub design, so the period which will going to repeat by so omega by vp, that is phase velocity of the wave. So if you take the ratio every 2 pi it will going to repeat. So why? Because we are going to design the filters based on the electrical length. So whatever the physical length of the stub, we are going to convert it to electrical length, that is beta L. Okay, so you can see here that is nothing but tan beta L. So this beta L is the electrical length, and that beta L we can replace this. So the beta in terms of omega and the phase velocity, which is nothing but the beta is equal to omega by vp. So that we can replace and we can find out the so frequency. So now this transformation, so which was introduced by the scientist which is who is called as Richard, and it is used to synthesize an LC network. So generally we have already designed the LC network, the lumped element LC network. So now this LC network which we can able to transform into open or short circuited transmission line stubs. How we can transform? So this is a transformation. So where we can have the reactance of the inductor, if you are using the inductor, series inductor, so that reactance we can equivalent to so j omega L, which is nothing but jl tan beta L. Okay, so and similarly we have the susceptance for the shunt capacitor, so that we can express in terms of this thing. So jbc, which is nothing but jc into tan beta L. Okay, so this is how we can transform that LC network into a transmission line stubs. So now the inductor, whatever we here we can took the expression, the same inductor can be replaced it as a short circuited stub of length beta L. So this is the electrical length, and similarly that characteristic impedance of the stub, which we can take it as the impedance of the L. Whatever the L value we will going to take, the same L it will act as a impedance of that stub. And similarly capacitor can be replaced inside it with open circuit stub of again length beta L. So which is a characteristic impedance of 1 by C, because it is in the shunt configuration. That characteristic impedance will be taken it as 1 by C. Now generally we have, whenever we take the normalized value, so we use the unity filter impedance. So that's not whatever we use normalized value, which will be always equal to 1. So now the cutoff frequency which we have taken earlier, omega by omega c, so that omega c equal to 1 by 1 radians per second. Similarly here the cutoff occurs at unity frequency for a low pass filter prototype. Okay, and also the same cutoff frequency can be used to obtain the richer transform filter. So you can see instead of omega c, when we transformed into a this omega plane, that is in the lump distributed element plane, we can take that omega equal to 1, that normalized value. So then we can able to find out what is the length of the stub. Now if you do that kind of calculation, you can see for this particular value of 1, so we'll be having the beta L, tan inverse of 1 is so pi by 4, that is 45 degree, right? So that tan beta L, which is equal to 1, so that is nothing but beta L, which is equal to pi by 4. Or we can say what is actually the length, so pi by 4 into 1 over beta, so 1 over beta is nothing but lambda by 2 pi. So now you can see what is actually the value of the length, so it is a lambda by 8. So for this unity filter or the cutoff frequency, which is the normalized value 1, we can get the length of lambda by 8. Okay, so now you can see, so that conversion how it is happening. So the same inductor jxl, which is series inductor, we can transform into a short circuit kind of stuff with the characteristic impedance. What is the value of L? It will be act as a characteristic impedance of the so transmission line, and the length which we got it is lambda by 8. Similarly the capacitor, we can taken it as a open circuited transmission line, and we can have the characteristic impedance which is 1 over C. Okay, so like this series and the capacitor, series inductor and capacitor, we can transformed into short circuit stub and open circuit stub. Okay, so now this is one transformation we can see, and another one which is nothing but Kuda's identity. So this here, so the different kind of the identities are there, so where we can use the redundant transmission line section to achieve more microwave filter practically. So the implementation, that is, so wherever it is required to transform so the filter the stub elements, we can use the redundant elements and we can transform it. Okay, so that sometimes we cannot able to physically realize the series stubs, so in that case we can use the parallel stubs and we can try to obtain the filter implementation. So that we'll going to see how we can able to do that. So now by using this identity, so what are all the things we need to do? So here the things, so physically separate the transmission line stubs, so where we need to see whether it is the series stub or parallel stub. So that we need to see, and we have to so transform particularly that particular kind of stubs. And this so transform series stubs into a shunt stubs or vice versa wherever necessary. If I want to transform series stubs to a shunt stub, that will be more physically realizable when we go to the fabrication point of view. So in that kind of thing, we have to convert that by using the redundant transmission line section, and also change the impractical characteristic impedances into more realizable values. That means, so when we have the characteristic impedance which is not feasible, so we need to convert that into more realizable values by adding this redundant transmission lines. Okay, so now here you can see the additional transmission line sections whatever we take redundant, so that are called as unity elements. That means the characteristic impedance normalized characteristic impedance which will be equal to 1. So that we need to take, and the length which which we can take it is lambda by 8 at omega c. So that is the cutoff frequency where it is there. At that frequency we have to take the unity elements, which is lambda by 8. Okay, so you can see these are the Kuroda's identities where we can transform if there is a. So if I say, for example, if I add this section 1 by z2 is there, similar kind 1 by z2, we can add some redundant elements which is 1. If it is that kind of thing, so if it is like this, so we can transform like this. If I have 1 by z2 and z1, so maybe this is inductor, or we can able to get that is again capacitor. Okay, so this parallel capacitance we can transform into series inductance. So this transformation we have to use in order to transform that parallel capacitance into a series inductance. Okay, and similarly if we have series inductance, if I want to transform it to shunt capacitance, so you can use this transformation. And similarly parallel inductor and series capacitor can parallelly can see the conversion how we can able to do that. Now if you come to the equivalent circuit, if you take the first one, if the first identity similar kind, if I take in terms of the stub or transmission line, let's say we have the open circuit stub, so we can have, and this z2 which will be represented as the capacitor, and then z1 which will be having this, so block box kind of thing. Now we can transform that by using this transformation. We can have, see here, so 1 by z2 if it is there, so we can have z2 by n square, and if I have z1 here, z1 by n square. Now corresponding to these values, so we can transform that into a corresponding, so the open circuit stub into a short circuit series stub. You can see at the left side we have open circuit shunt stub, so it is similar kind here, it is a shunt stub. So we have like this. So this is a open circuit kind of stuff. Okay, and we have the z2, so this, and z1 of this we can convert into a, so series kind of thing. Okay, so now we have here, so the value of z1 by n square, and similarly here this z2 we are transformed into a short circuit series kind of thing, whatever shunt is there. Okay, so the same thing we have transformed into series kind. So that is what we are doing here. Okay, so this is, sorry, this is z1, this is z2. Okay, so similarly we can do that. So even whenever we require this kind of transformation, we can able to do. So now these are the transformation where we can able to do the, so Ruda's identity we can use, and we can transform the, so corresponding steps. Now we'll do one problem such, so that how we can able to transform the filter elements that is lumped into a, so distributed, and also arrive the final design. Let us take one problem. Okay, so you have to design a low pass filter. Okay, design a low pass filter, so using microstrip line. Okay, using microstrip line. So now the cutoff frequency is 4 gigahertz. Okay, and then impedance is 50 ohm. So then we have to use n equal to 3, the third order, so filter, and with there is a 3 dB equal ripple at the pass band. Okay, so now, so this is what we have the specification. We need to design a low pass filter using microstrip line, that is nothing but a kind of a stub design. So now you can see we have the 3 dB equal ripple for n equal to 3, cutoff frequency is 4 gigahertz. Now from the filter table, First we need to design a lumped element. Okay, so we can see the 3 dB ripple. So here n equal to 3. So what are all the element values? 3.34, 0.7117 and 3.34. So these are all the three filter elements we got from this table. So that you can write it as, so the values are G1 which is equal to 3.3487, G2 which is equal to 0.7117 and G3 which is equal to again 3.3487 and G4 which will equal to 1. So that is always the load will be normalized to 1. Okay. So now we need to convert this into a, so first we need to find out the filter values. That is, so we generally take the low pass filter, first inductor and then capacitor, so and then inductor. So this is the three element for the n equal to 3. Okay. So now we have here, so the source resistance which is equal to 1 and load resistance which is equal to 1, and this one is 3.34, so 87 the first element value L1, and C2 which is equal to 0.7117, and then G3, so which is nothing but L3 which is equal to 3.3487. So this is a filter circuit which we have in the, so lumped element design. Now we can see this inductor, series inductor, can be transformed into a, what we can call it as the stub kind of thing. So now you can see the series inductor can be transformed into a short circuit stub. So it is in the series. We can call it as, so series short circuit stub. So of length L. Okay, and this Z naught of this one, which is nothing but the value of L. So this whatever we have transformed this, which is in terms of L. So now in similarly, so we can have another inductor here. So that also we can take it as series 1 and the load. Okay, so this is the load value 1 and this is again the series value L, which is having a Z0 which is equal to L3, and this one is L1 because we have the value of L1 is here and L3 is here. Now similarly, so the second element we can transform into a open circuit stub. Now we can see here, so earlier which I shown, so this inductor can be transformed into a short circuit stub, and capacitor we can transform into a open circuit stub. Okay, so that is what, so that we have done here. So now we have the characteristic impedance which is Z0, which is equal to the C2, 1 over C2. Okay, so now that's how we transform this one. So now you can see the series stubs are not more realizable in the microstrip kind of thing. So now we need to convert these series stubs into a short circuit shunt stubs, or we can transform it into a short circuit open stubs. Okay, so now we're going to convert this into a short circuit, so that is open circuit shunt stub. So this series short circuit stubs will convert into a shunt open stub. Okay, so that we're going to do. So now if you do like that, we need to add a redundant elements. In order to convert that, we need to add a redundant elements because this is the only single value, and if I need, if I one more redundant value if I do, then we can use the crudas identities and we can able to transform those. So now how we can add that? So we can add the elements which has unity elements, that is the Z0 value, so which is equal to unity elements. So now we can take this one as, so Z0 which is equal to 1, which is the redundant element we are adding. Now we have the series element which is having the length L, and Z0 which is equal to L1. Okay, so then we have again the capacitor as it is, which is there. Okay, so the capacitor which is Z0 equal to 1 over C2, so that is nothing but 1 over 0.7117. So we can find out the value of this. Again we have C series kind of thing, and we have to add the another redundant element. Okay, so here again I am adding the another redundant element. So this will be equal to 1, and this will be having the L2. So the length of this stub is L, and L, the Z naught characteristic impedance, which is equal to L2. Okay, so which is equal to same 3.3487 for both. Okay, so now we need to do this, whatever we have the, so the first element redundant element 1 and another, so series stub. So this we need to convert into a shunt open stub. And similarly here you can see this series inductor, or sorry, series stub, and then another redundant element. So this Z not equal to 1, which we added, so that we need to convert it to shunt stub. So open circuit shunt stub. So now how to convert? So now we know the CUDA's identities, you can see here. So if you have this kind of thing, so you can see here the series elements and this Z2. So we have to use this second one because we have the series element and another short circuit series element. Now we have to use this transformation and we have to do that. So now if I do that, so you will going to get, so this whatever Z1, so which will be transformed here n square into Z1. Okay, so now we can treat this one as the Z1 and this one as Z2. Okay, so whatever the shunt series stub is there, short circuit stub, we can treat it as this one as Z1 and this one as Z2. Now we have the series Z1 and we have Z2 here. Okay, so this will be transformed into what? So we'll be having n square. So what is the identity we have here? So you can see here n square Z1, so and then 1 over n square Z2. That is, so we have the transformed value n square Z1, it is first one. Then we can have the capacitor which is having a, so 1 over n square Z2. Now in our case we do not assume it as an inductor, it is a, so some element which is having a Z1 value. So now that Z1 equal to 1. So now if I transform this one, so in our case if you transform that, you will going to get n square Z1, and another one is, so this Z2 if I take, which is nothing but 1 over n square Z2. Okay, so this is what we will going to transform, and we will going to get, so that shunt stub and shunt open circuited stub. So this is what we will going to get from, sorry, here this is connected. Now, so whatever we have the series kind of thing, okay, so whenever we have the, here the unity element is there Z1, and we have the series short circuit stub. So now this can be transformed into a, again, so we have the shunt stub which is having a value of, so we'll going to get this as Z2, right? So this will be having 1 over n square Z2, the value of this one, and then so we'll be having a, so Z1 which is nothing but n square Z1. Okay, so that is what we'll going to get here. Okay, so if I transform this one, you will going to get the shunt opens circuited stub. Now if I do that, so we will going to get, so that n square is nothing but, you can see the n square value, the n square value is 1 plus Z2 by Z1. Okay, so 1 plus Z2 by Z1, if I calculate that, n square value 1 plus Z2 by Z1. Now you can see the Z2 value we know in our case, that is 3.3487 divided by Z1 is 1. Now my n square is 4.34. Okay, we need to substitute in this case and we have to convert it. Now if I do the conversion, this value it will going to be z square in n square into z1. Now n square is 4.34 and z1 is 1. Sorry, so we need to convert this into here. So this is z1 and this is z2. Okay, so now z2 is, so the z2 value is, so 3.34 and n square is, what is the value of n square? It is 4.34. So now so here, so z1 only, z1 only, so this one is z2. So that is it is, so here we will going to get to 4.34 into 1, because we are, so this I'll rewrite again. Whatever we have, so we have the unity element which is having z1, and we have the short circuit stub which is having z2, so which is equal to 3.3487. This will be 1. Now we need to convert this into a shunt stub. Okay, so this is a shunt stub, and we have, so once we convert this z1 it will go to this side, so which will be again, so n square into z1, and this one will be getting n square divided by z2. So this is what the shunt circuit stub transformation it will happen. Now n square we got it as 4.34. Now if I convert that, which will be going to give 4.34 by, so z2 value is 3.34 and n square z1 is, so this is 4.34 into 1. So we will going to get 4.34. This is the value conversion we will going to get it. So similarly, if I do that other side also, so in the other side of the inductor, so where we have, in the similar way we have to convert that. Now once we convert that, so we'll going to get the final circuit as, so like this. So we'll be having one, and we have converted that into a short, so open circuit shunt stub. So this is we will be having, so now z0 which is, so we can see the z0 value is this one, that is the uh, whatever the ratio we're going to get. So we can calculate what is the ratio of this. So that ratio we're going to get the z0 of this shunt open circuited stub. So that it will going to be, so around 1.29. Okay, and then we have the, so another element which is z0, which is we have converted here. So this unity element. Okay, and then we have that one as 4.34. Another one we have, so capacitor which is already there, so that is open circuited stuff, that z0 will be equal to 1 over c. And similarly, so another term, so we're going to get another shunt stub, shunt open circuited stub. Okay, so and then finally we have here z0 again. So this section is for capacitor, and then this z0 before that, which will be having again 4.34. That if we convert that, so this short circuited and unity element, so in the load side. Okay, so this is z0 equal to 1 and this one is, so that is z which is equal to L3 value which we got in the load side. If I convert this one, you will going to get the unity element here and the stub element, which is nothing but again, so we will going to get z0 of the stub which is equal to 1.29. Okay, so finally we're going to get the circuit which is, so like this. Okay, so I'll write clearly again. So we're going to get, so three stubs which are shunt stubs. Okay, So first one is, so this is a shunt stub which we have converted value, which is z naught equal to, so 1.299. So this is one section of the transmission line, and another section we have the unity element which is z naught equal to 4.34. Okay, and then another one we'll be having a again shunt which is z naught equal to 1 over c, and this is another section we have. And then so another section we have z naught again which is equal to 4.34 unity element, which we convert that the load side value into load side series stubs into a this transformation. And this one is the third one which is equal to 1.29, same as this one, shunt stub. Okay, so then we have the load. So we have five sections. One is the first one is the shunt stub open circuited, then the characteristic impedance 4.34 unity element, then again the capacitor shunt open stub, again unity element, again e, so z naught. Okay, so like this we have the so filter design which is having a stubs. So this is we have used the shunt open stub. Now these are all the normalized values. Then we if you multiply that, you will going to get the absolute values which is equal to 50 ohm. And then we have the stub value. You can convert that stub value, so 1.299 into 50 ohm, so that is we're going to get it as around 64.9 ohm. And similarly we have this one. So here z not equal to 4.34, so that if you do you will going to get 217.5. Okay, so then again another stub which is z not equal to 1 over c, so that we got it as so around 1.405. So if you take here 1.405, you're going to get, so that stub characteristic impedance which will be going to get it as 78.3 ohm. And again another unity element which is z naught, which is same as this one, 270.5. Okay, and then again another stub, so which we have taken it as same as this one, which is z naught equal to 64.9. Okay, so then finally we have the 50 ohm load. So this is how we're going to design that. And if it is, so if you see the microstrip version, it will look like this. This is a first shunt open stub. Okay, and then we have the characteristic impedance of 217.5, so this section. And this one has a characteristic impedance z naught which is equal to 64.9. Again we have the shunt stub open stub, this section which is having a z naught equal to 78.3 ohm. Okay, and then we have z naught equal to 217.5, this section. Again we have the shunt open stub. Okay, and then we have the load. Here it is 50 ohm. Okay, so and then here it is 50 ohm. So this z naught which will be equal to again 64.9. So this is how the filter stub realization in terms of microstrip. This is a top layer and there is a substrate behind that. Again there is a ground plane. So like this is a filter where we get the low pass filter which is third order. Okay, so we're going to get so some ripples kind of thing, so 3 dB ripple, and then we're going to get like this, the response and cutoff frequency which is equal to 4. So this kind of, if you use this the same thing you can able to simulate in AWR. If you do this one, you will going to get the response like this. Okay, so this is how the conversion which happens from lumped element to the stub design. Okay, so even you can take another kind of problems and we can do that. So I'll just post it that as assignment and you can do. If you don't get, I'll send the solution. First you can submit as assignment. Not two problems I'll send. Okay, so this is about the stub filter design. So if you have any queries you can ask. Any doubt? Sure. Sure? Any doubt? Pastry? No. Fish? Hello? Okay, so now you're not talking. It's a waste of time. Okay, so we'll stop here. So this completes your filter unit, and all the five units I have completed.